Hey everyone and welcome to my channel. I'm the online maths tutor and I'm going to post a few short videos about Year 11 and Year 12 level mathematics, particularly in relation to the Australian HSC course, and if I get enough positive feedback, I'll keep on going. So I'm going to start off by teaching calculus. Specifically, if you're a high school student who's learned a bit of curve sketching, algebra and trigonometry, but hasn't exactly gotten up to dabbling in more advanced maths like calculus, these videos are for you. So what is calculus? It's basically the mathematics of change, looking at what we call instantaneous change, instead of just observing static things. With calculus, we can see and analyze how stars move, how objects fall, basically everything that changes around us. When we talk about differentiation, which is one of the two core components of calculus, the other being integration, it's basically looking at the changing steepness of curves. What I mean by that is, let's say you've taken some cold juice out from the fridge on a sunny day, and you're measuring the temperature at which it slowly adjusts to the outside room temperature. What I've got here is a graph of that, of its temperature versus time, and we can see its temperature increases from 5 degrees Celsius all the way to 30 degrees Celsius over the span of 10 minutes. And with basic maths, we can figure out the average change in temperature per minute from start to finish, which is going to be the gradient here, which we can calculate as the rise over run, which is 30 minus 5 over 10 minus 0, which gives us 2.5 degrees per minute. But if we want to see a more useful property, and that is the instantaneous rate of change, we're going to need what's called a derivative. We want the gradient of a point on the curve, so we can actually figure out how the temperature is changing per second at that one point. This tells us basically how fast the temperature of our juice is increasing at that certain second. And to do this, we draw a tangent at that said point. And this actually reflects how steep the curve is, or how fast it's increasing. And basically, this gradient of this tangent will tell us how fast the curve is increasing at that point, or how fast our juice is warming up. And what our derivative basically is that it's a function. It's a function f dash of x. And this basically is, if let's say our original function was f of x, our derivative function basically denotes the gradient of the tangent to our function y equals f of x at every single point on the curve. So what I mean by that is, say this point is like x equals 3, or t equals 3. If we sub in this value of 3 into our derivative function, we'll get the gradient of the curve at this certain point, of the gradient of the tangent to the curve at that point, which this looks like approximately a third. So our derivative function would give us a third if we plugged in x equals 3. So obviously, the easiest graph to use to calculate our derivative is going to be the linear graph. So, because the gradient at every single point is always going to be the same. So if this graph we have y equals 2x, the derivative of this graph is just going to be y equals 2, because the gradient at every single point along this curve is y equals 2. Remember, our line can be written in the form y equals mx plus b, and our m is just our gradient, which is 2. But when we look at more complicated functions, that's when we'll get stuck. We need to consider something called the limit. For example, this graph here, how can we calculate the gradient of this graph? It's not a linear graph, it's a very complicated function. And to do this, we can just think of it as a gradient first. So what we can do is, we say this point, we measure the gradient of this curve between 2 points first. Let's say these points are x, and this point x plus h, which is h units to the right of x. This will correspond to a y value of y equals f of x, and y equals f of x plus h. And this forms a gradient here. And we can say this gradient, the value of this gradient is going to be the rise over run, which is going to be f of x plus h minus f of x, which is the rise, the value between these 2 points, and x plus h minus x, which is the run. And that gives us this expression here, because the x's on the bottom will cancel out. But let's consider this. To find the gradient of a single point on the curve, or the tangent to that point and the gradient of that, h will slowly, let's say h slowly becomes 0, comes closer and closer to 0, so that this second point becomes closer and closer to x until it just becomes x. So at that point, it will just be one point, and we'll get the gradient of the curve at that certain point. So we can say, for a derivative, the formula will be limit as h approaches 0 of f of x plus h minus f of x all over h. So this funky little symbol here basically means as h approaches 0, you sub in the value of h equals 0 and you'll find the derivative. And so we've generalized the formula for finding the derivative of more complicated curves. And this is actually called differentiation by first principles. So let's try to apply what we just learned, this generalized formula for finding the derivative to some curves that we know of, such as y equals x squared, a very common one. So we have, this is going to be a parabola with its vertex at the origin. It's obviously not to scale, but it gets the point across. So here we have f of x equals x squared. Our first principles tell us, our differentiable by first principles formula tells us that f dash of x is equal to limit of h approaches 0 of f of x plus h, which is equal to x plus h all squared, because we sub in this x value here, and we sub in this x plus h value for where the x was originally. I would suggest writing these out as a beginner tip if you're new to differentiating by first principles, because it's very common to make a mistake like this. So you write out the wrong function value and you'll get the answer wrong. So f of x plus h is x plus h all squared minus x squared, which is our f of x all of h. So what we can do here is expand the top minus x squared all of h. And a very common mistake that students will often make is forgetting to carry the x limit h approaches 0, this expression all the way through. Because you haven't actually done this operation yet, you have to keep writing it all the way through until you actually sub in the value h approaches 0. And why can't we just do it straight away, you ask? Because if we do it straight away, we can see that our denominator is h. So if we have a denominator as 0, our current understanding of maths tells us that this value is going to be undefined. So obviously, we have to get rid of this h from the denominator somehow, which is what you're going to see as we progress along with this question. So we can keep writing limit h approaches 0 of x, and we can cancel out the x squareds at the top. And this leaves us with 2xh plus h squared all over h. And now we can factor out the h and cancel it from top and bottom, which gives us limit of h approaches 0 of 2x plus h. And now we can finally evaluate the limit, which is going to be 2x plus 0, which is 2x. So what did we just find? We just found the derivative function of this curve y equals x squared, f of x equals x squared, as the derivative is being 2x. So what can we do with this? Let's say we have this point x equals 3, and we want to find the gradient of the tangent to that point. Using our first derivative, we can figure it out as 2 times 3, which is going to be 6, because we sub in the value of x equals 3 to our derivative, which is 2x, and it's going to give us a gradient value of 6. And now, let's apply it to a very similar curve, which is going to be y equals x squared minus 3. Now this curve is basically exactly the same as the curve we just did, but a small difference is that it's been shifted down vertically by 3 units along the y-axis. But since it hasn't been shifted along horizontally, let's propose a theory that at x equals 3, it should still be giving the same value of the gradient to the tangent of the tangent that is tangent to that point on the curve. So if we evaluate our derivative by first principles, it should, in theory, be the same as our derivative for y equals x squared. So I'm going to give you guys a try and try to figure out the derivative of this function and see if it is the same as y equals x squared. So now go and have a shot at this question. Alright, hopefully you guys managed to get an answer. So let's try to do this now. We can define our f of x as x squared minus 3, now f of x plus h as x plus h all squared minus 3. So now our first principle, our first derivative, is going to be limit of h approaches 0 of x plus h squared minus 3 minus brackets of x plus x cubed x squared minus 3. Making sure to have this in brackets because this is the entire f of x term and the whole f of x term is subtracted all over h. And we do the same thing we did before, which is expand the top, which gives us x squared plus 2xh plus h squared minus 3 minus x squared plus 3 all over h. What we can do is just cancel out the x's, x squareds, and cancel out the 3's. And we're left with this, which is exactly the same as what we had up above. And we know that's just going to give us 2x. So yes, the first derivative is the exact same. So this is going to be equal to 6. The gradient of this tangent is equal to 6. But what would happen if we actually shifted it horizontally? Well, that's a good question. And that's slightly harder to find by first derivatives. So this is a problem you could try at home. Is what would be the first derivative of function x plus 2 squared, which is this parabola shifted to the left by 2. And this is a bit trickier to find by first derivative, first principles. So I would suggest expanding it first and then giving it a shot. So let's consider a final function, which is y equals 3x cubed. This function is a cubic curve. So it's going to look something like this. With, let's say this point is x equals 1, y equals 3. Let's say we want to know the value of the gradient of the tangent to this curve at that point, x equals 1. So we know f of x is equal to 3x cubed, that's our function of x, and f dash of x, sorry, not f dash of x, f of x plus h is going to be 3 outside of x plus h cubed. So our derivative by first principles we can calculate as 3x plus h all cubed minus 3x cubed all over h. Now, cubic expansions is something that you probably haven't learnt to memory at this point, but we can easily figure it out. And we can do that by just expanding it as, we can write it as limit of h approaches 0 of 3 outside of x plus h squared times x plus h. So we just expand both of these, and that should give us an expanded form of x plus h cubed. Limit of h approaches 0 of 3 outside of x squared plus 2xh plus h squared outside of x plus h minus 3x cubed all over h. Remember, we're still trying to cancel out every single term that doesn't have an h, so that the main goal is to factorize out an h, so that we can cancel the h from top and bottom, so that we can actually apply the limit. So if we continue our working, we'll get 3 outside of x cubed plus 2x squared h. This is by expanding what's inside of these two brackets, plus xh squared plus x squared h plus 2xh squared plus h cubed minus 3x cubed all over h. Now I know this looks like a lot of terms, but what we can do is just gather the like terms, because we see there's two different like terms here. There's 2x squared h and x squared h here, and there's xh squared and 2xh squared here. So gathering those terms, we get x cubed plus 3x squared h plus 3xh squared plus h cubed minus 3x cubed all over h. What we have here is our cubic expansion of x plus h, or cubed. Now we just keep expanding, and hopefully some terms will be able to cancel out, and we can see that it's going to be the case because we have 3x cubed here that will cancel out, and we're just going to be left with limit as h approaches 0 of x squared h plus 3xh squared plus h cubed all over h. Factor out the h, so we're left with 9x squared plus 3xh plus h squared over h. H's will cancel out, and we're left with this, x squared plus 3xh plus h squared. And we can finally apply our limit to get 9x squared plus 3x times 0 plus 0, which is just going to be 9x squared. So our derivative of this function, 3x cubed, is just going to be 9x squared. Now we can finally answer this question. The gradient of this tangent is going to be 9 times 1 squared, which is going to be 9. It's obviously very steep, and you can see it's going to be steep. And yeah. So now I'm going to propose a few homework problems, and solutions for these problems will be uploaded along with the next video I make. So these are going to be somewhat challenging, so if you can't figure it out, don't worry, just check out the solutions in the next video. So first one, which is an easy warm-up. Doing all these by first principles is to sketch x cubed minus 3x, find its derivative, then state the gradient of the tangent to the curve at x equals 3. The second problem, which is a bit harder, is find the derivative using first principles of y equals 1 on x. And lastly, which is a challenge problem, is find the derivative of y equals root x. And this is tricky, so I'm going to give a hint, which is to consider rationalizing the numerator. So hopefully you guys can give these questions a shot, and I'll see you in the next video.